Okay, momentum. And you will find that these ideas are really a new way of looking at things that we've already thought about. But it's a new enough way of looking that it will seem quite different, and it will give you some it gives you insights that you wouldn't necessarily see as easily if you were doing things the old way. So first, a definition. Momentum, we use the letter P for momentum. M is already taken with mass. And the momentum of an object is a vector, and it's just mass times the velocity. And remember, anytime we take a plain old number times a vector, the result of that multiplication is a new vector in the same direction, but with a different magnitude, a magnitude that's changed by this factor of m. Okay, so we want to think about change in momentum because the interesting things all deal with changes in motion, accelerations, and all that stuff. Change in anything, delta anything, is just the final value minus the initial value. And so there's final value of momentum, initial value of momentum. Now, when we're talking about changes in momentum, we could think about momentum changing because the mass changes between the initial state and the final state. But for now, we're just looking at the simpler case where the only kind of changes we have are changes in velocity. Those are the only kinds of changes that will make momentum change. So final value of momentum minus initial value of momentum. And you can rewrite that by factoring out the m, but then what have you got here? You've got final velocity minus initial velocity. Well, final anything minus initial anything, we can just write as change in that thing. So what do we have here? Change in momentum is just mass times change in velocity. Let's think about rates of change. How quickly does the momentum change? In other words, divide this whole equation by delta t. Divide this side and divide this side by delta t, where delta t means the length of time it took to make this much momentum change. And similarly, you could just as easily think of delta t as the time it took to make this much velocity change, because this much velocity change is how you get this much momentum change. But we've seen this delta v over delta t, we've seen that before. That's just our definition of acceleration. And now mass times acceleration, go back to Newton's second law, mass times acceleration gives you the net force. So what do we have here? Here we go. Rate of change in momentum equals net force. Now, rewrite that just a little bit and say that is multiply both sides by delta t. So here on the left side, you've got a delta t divided by delta t, so they cancel out, and all you're left with is delta p. Equals net force times the time. So now there's yet a third way you can and should think about this this delta t. Right? I already said that delta t was, you can think of as the amount of time it took to make this much momentum change, and it's also the amount of time it took to make the velocity change that gives you this momentum change. And it's also the length of time during which this force was acting, because as long as this force is acting, there is acceleration, which changes the velocity, which changes the momentum. Anyway, this equation here is called the impulse momentum theorem in the textbook. I'll just call it IMT for impulse momentum theorem. Momentum, that's obvious. Impulse, what is the impulse? Usually when we use the word impulse, we're referring to that product of force and time, times the length of time that force was acting. But because of the impulse momentum theorem, the impulse is just numerically equal to this, the change in momentum. So you could say that change in momentum and impulse are really the same thing. They're numerically equivalent to each other anyway. So I might use those terms interchangeably, change in momentum and impulse, because after all, they're always referring to the same number. They're equal to each other. So what is the significance of this? Well, one example where this shows up is if you're trying to hit a tennis ball or a baseball or a golf ball. In all those cases, you're taught to continue your swing even after you feel that the ball has left the racket, no longer in contact with the racket. You're always taught to follow through and not just stop the swing as soon as you feel the racket and ball in contact with each other. The reason you do that, the reason you follow through instead of stopping your swing is this. This is the reason, because when you're hitting the ball, what's the point? What are you trying to do? You're trying to get the maximum possible change in the ball's momentum. And for any amount of force that the racket applies to the tennis ball, you'll get a bigger change in momentum. In other words, a bigger impulse if you have that force acting for a longer period of time. And if the racket is in contact with the ball for a longer period of time, then the racket is pushing on the ball for a longer period of time. And therefore, the force from the racket on the ball applied for longer time gives you more change in the ball's momentum. Another example of this is airbags. When you're in the car and you come to a very sudden stop, there are basically two ways that you could stop. When you stop, what happens? Well, of course, you have a big change in momentum. Right? Previously, you had some velocity, and after the stop, you have no velocity. Or to put it another way, previously you had momentum, and after the car stops, you have no momentum. So there are two ways to get that same amount of momentum change. Either a lot of force applied over a short time, or a smaller force applied over a longer time. If you just hit the steering wheel or the dashboard, you're hitting something hard that is only slightly elastic. So it will bring you to a stop very quickly. So this will be a small number. So in order to get however much momentum change there is in changing from your previous speed to zero speed, if you got only a small amount of time, then the force has to be big. The airbag is a little bit squishier, so it as you come to a stop, you're able to squeeze on it a little more. It takes you a little more time to come to a stop. So you get the same momentum change either way, because either way you had the same velocity and momentum initially, and in the final state, either way you have the same final velocity and momentum, 0. So you could get the same amount of momentum change if it happens over a much greater length of time, but then if this factor is bigger, this one gets smaller. You can get the same momentum change with less force if you just apply that force for a longer period of time. And applying less force over a longer period of time is what the airbag does to you. And less force means you get hurt much less. But you'll still get some nasty bruises, but probably no broken bones or anything even worse. Okay, now, next thing about impulse or change in momentum is something that was mentioned at the very start of chapter 9. Let's think about this. Let's imagine that some impulse is being applied to something that is, it's feeling a force for only a short, well-defined length of time. So just make a graph of force versus time. And let's say that, keep it relatively simple, let's say it's a constant force for this much time. So this, from this time to this time, that's just the length of time that the force is being applied, so that's what we mean by delta t. And there's the amount of force, we'll call it just plain F. So what's the impulse in that case? The impulse is just force times delta t. The symbol that we usually use, the symbol that the book uses for impulse, is a capital J. So we have that, but look, delta t corresponds to the length of this rectangle. F corresponds to the height of the rectangle, so what we have here is height times width, in other words, the area of this rectangle. In other words, impulse, or change in momentum, same thing, impulse is just equal to the area on a graph of net force versus time, the area between the force line and the time axis, and then between the initial and final times. That's just about how the textbook defined impulse in the first place, as the area between the force line and the time axis. We've seen this sort of thing before, right? Way back in chapter 2, when we had a velocity graph, their areas on that velocity graph corresponded to displacements. Same kind of thing here. Areas on this force graph will correspond to impulses, changes in momentum. One extra thing to think about here. Go back to our impulse momentum theorem. Right? A length of time is always a positive number. Let's say that this net force is negative. let's say that this net force is pointing in the negative direction, whatever you have chosen to be the negative direction. Well, positive times a negative number gives you a negative number. Right? The change in momentum points in the negative direction. So that means if we have a force versus time, a net force versus time graph, where the force is negative, well, if you have a negative force, that means you have a negative impulse, but it is still the case that that impulse is the force times the length of time that the force was acting, which is now minus F times delta T. But this F, forget the minus sign, just the F itself now means the magnitude, which corresponds to this length. Delta T corresponds to this length. So it's still the case that we have an area in here. It's just force times delta T. Remember, there's delta T. Force times delta T is just height times width of the of that rectangle, the area of that rectangle. So for a negative force, the change in momentum or the impulse is just the area times minus 1. And the important point here is that this relationship between area and impulse, this relationship between area and change in momentum, is true no matter what the force line looks like. Say for any net force, no matter how it changes as time goes by, it's still the case that the area between the force line and the time axis, and between the initial and final times when the force was present, it's still the case that the change in momentum, which is equal to the impulse, is equal to the area between the force line and the time axis. And if the force is negative, it's still the case that the change in momentum, which is equal to the impulse, will be that area times minus 1. Let's look at one specific example of how that works. Let's say you've got say a ball is moving in the positive direction, positive initial velocity, say 20 meters per second. Or let's keep it simple here. Let's say just ball is just rolling along a track. So it's 1 meter per second. And then the little kid is watching the ball roll, and then the kid gives it a brief push. In other words, impulse is applied to the ball. So the ball is going to go faster, of course. How much faster? What is the final velocity at the end of the push? Let's say the mass of the ball is 150 grams. We usually want to work, whenever we have a mass, we usually want to work in kilograms rather than grams, because if we want forces to always come out in newtons, we must use kilograms for our masses. So maybe we want to call this 0.150 kilograms. Okay, so the initial speed, 1 meter per second in the positive direction, and then the final velocity, it's going faster in the same direction, but we don't know how much faster. But let's say we know something about the force. The kid's push really amounts to the same thing as the net force in this case. So we can use that. To figure out the impulse, which, remember, is numerically equal to the change in momentum. And if we know the change in momentum, we'll be able to figure this out. So let's say the force looks like this. Not a constant force, but for half of the time when the kid is pushing, the force is getting stronger, and then the other half of the time when the kid is still pushing, the force is getting weaker, and the kid pushes for this long, and let's say that this length of time here delta t is 6 milliseconds, not 6 seconds, 6 milliseconds, 6 thousandths of a second, or 6 times 10 to the minus 3 seconds. And let's say that the maximum amount of force that the kid applies here is, let's say, 200 newtons. Let's make it 400 newtons, okay? So what do we know? We know that change in momentum is just mass times final velocity minus mass times initial velocity. Velocities and momentum are vectors. Let's not forget that, because that means their sign and direction are important, and we cannot ignore those. But change in momentum is the same as impulse, which, among other things, is just the same as the area between the force line and the time axis. In this case, the area is a triangular area, and go all the way back to geometry. The formula for the area of a triangle is 1/2 length of the base times length of the height. So that area then is 1/2 length of the base. Length of the base is just the length of time. That's 6 times 10 to the minus 3 seconds. And then times the height, which is just the maximum value of the force, that's 400 newtons. So let's multiply all those numbers together. One half times 6 is 3. And then 3 times 4 is 12. And then 10 to the minus 3 and 100 there, you'll come out with 1.2 for the final number. 1.2 what? Well, seconds times newtons, or newtons times seconds. And that's actually a reasonable unit label for an impulse or a change in momentum, because if you play around with this, you actually can show that this this unit label is the same as a normal momentum unit label, which would be a mass times a velocity. Mass, kilograms, velocity is meters per second. The unit label newtons per second is the same as the unit label kilograms, meters per second. Has to be, because this number here is not only an impulse, it also represents a certain amount of change in momentum. So just write out in detail this momentum change. Mass times final velocity minus mass times initial velocity equals 1.2 kilogram meters per second. Now insert the numbers that we know. Mass is 150 grams or 0.15 kilograms. I'm going to factor that mass out of the equation. So that's 1.150 kilograms times V final, that's the thing that we're trying to find, minus V initial, which was 1 meter per second, equals 1.2 kilograms. Okay, so let's see what we've got here. We want to solve for this. The first thing we can do is divide both sides of the equation by 0.15. Kilogram meters per second, 0.15 kilograms. And remember, unit labels you treat just as if they were algebraic variables. So here's a kilogram in the numerator, kilogram in the denominator. They cancel out. And the only unit label left is meters per second. That's exactly what we want because we're trying to find a velocity. Anyway, okay, so we're almost there. Let me make one little change here. So, we're going to get a really goofy number unless I make one little change here. Let's say that the final, let's say that the maximum force the kid applied was not 400, but just 40 newtons, 10 times smaller. So that makes this 10 times smaller. Now it's 0.12. 0.12. So now 0.12 divided by 0.15, that'll be equal to 4/5. Or 4/5 is the same as 8/10 or 0.8. 0.8 meters per second. 0.8 meters per second equals the left-hand side of the equation, and remember we divided the whole equation by 0.15 kilograms, so that cancels out this, and after we do this division, all that remains on the left-hand side is V final minus 1 equals that. So, final answer almost, V final minus an initial velocity of 1 meter per second equals 1.8 meters per second. In other words, the final velocity must be 1.8 meters per second. So in other words, the kid's impulse almost doubled the speed of the ball. It went from 1 meter per second to 1.8 meters per second. Okay, and in the assignment, you'll be doing the same kind of thing, figuring out you're given a graph, you figure out the impulse, and then once you know that, you can use that number to see how a velocity has changed. Quite similar to this. Right? As time goes by, we'll see situations that are less and less similar, at least superficially. They might seem less and less similar, but nevertheless, they'll all really be the same thing because you'll be doing the same things. You'll be asking the same questions.